Now let's consider another type of deformation, which is angular deformation. Let's say we have a fluid particle here. At time t plus delta t, it becomes something like this. So how do you define this angle? Do you consider it to be an angular deformation of this angle? Or is it simply a rotation? It seems both make sense, right? So how do we define that? Well, spoiler, if our fluid particle indeed behaves like this, then this angle is comprised of two parts, both a rotation and an angular deformation. So now let's talk about how we define that. Let's make our fluid particle at time t plus delta t to overlap with our fluid particle at time t, okay? So you can say that we have subtracted from the velocity of every point by the velocity of u x1, x2, okay? So the effect will be that the fluid particle at time t plus delta t will overlap with the fluid particle at time t at this point, x1, x2, okay? Now, we see that there are two angles formed, right? So how can we calculate these two angles? Let's first consider this angle. This angle, let's call it to be alpha, okay? So let's first ask the question, how was the angle alpha formed? Why is there an angle alpha? Do you agree that the angle alpha is formed because of the fact that the U2 here is bigger than the U2 here, right? If we pick out this side, the U2 here is bigger than the U2 here, then this thing will become something like this, right? So how can we represent this angle? This angle basically represents the change of U2 in the x1 direction, right? In the x1 direction. Well, to be more exact, to find this angle, we need to calculate the length of this thing, which will be this times this, right? This dimension is dx1. So this length will be this times dx1. And we also need to divide by dx1 to get the tangent of this angle. And since the angle is very small, then we can argue that the tangent of this angle is just this angle itself. So actually, this angle is this thing times dx1 to get this, and divide by dx1, and we get back this to be this angle alpha. So how can we represent this angle beta? Same reasoning, right? This beta is formed because of the fact that the U1 here and the U1 here can have a difference. That is, the U1 can have a difference in the U2 direction. So this angle can be represented as du1 dx2. du1 dx2. Okay, so this is this angle. Our question remains, how do we define a rotation and an angular deformation? Well, it appears in the picture that this angle and this angle, which is du2 dx1 and du1 dx2, are not of the same value, right? So we make them the same value. We artificially make them the same value. Something like this, okay? So this is alpha and this is beta, right? So we make both the angles, this angle and this angle, to be what? Half alpha plus beta, right? Half alpha plus beta, which is half du2 dx1 plus du1 dx2. Half du2 dx1 plus du1 dx2. This is this angle, which has the same value on this side and on this side. Okay, so what will be this value? This value. the value of the angle which we have here minus the angle that we artificially make them equal on both sides. This angle is just the whole angle, which is alpha, which is du2 dx1, minus this angle, right, which is this thing. So if we use this thing minus this thing, we'll get this thing. So what will be this thing? This thing will just be half du2 dx1 minus du1 dx2. Do you agree? Okay, so now I'll tell you. This part, which we artificially made to be equal on both sides, is what we call to be epsilon 1, 2. Epsilon 1, 2. You see, we call it epsilon 1, 2 because it involves two directions, right? Both the two dimensions and the two velocities on the two dimensions. So this thing is called epsilon 1, 2. Also, you can see epsilon 2, 1 is what? Epsilon 2, 1 is half du1 dx2 plus du2 dx1. First, it's of the same value as epsilon 1, 2, right? So you see we have epsilon 1, 1 and now we have epsilon 1, 2, right? So later, this thing will give us a tensor, and that tensor will be a symmetric one, right? Also, what is epsilon 2, 1 anyway? Well, this angle is epsilon 1, 2, right? So this angle is just epsilon 2, 1. So obviously epsilon 2, 1 will be of the same value as epsilon 1, 2, right? Because we artificially made them to be equal. Okay, so this is epsilon 1, 2, which we call to be the angular deformation. Angular deformation. And what's this part? Well, this part is just the rotation, right? This part we call it to be omega 1, 2. Omega 1, 2. Well, if you see omega 2, 1 will be what? Omega 2, 1 will be half du1 dx2 minus du2 dx1, right? Which will be the opposite at omega 1, 2. So if we write the omega tensor out, we expect to get an anti-symmetric tensor, right? Okay, so every movement or every deformation plus rotation, you can say, we can divide it down into two parts. First, we have, say this thing. First, we have the angular deformation, which is something like this. And then we have the rotation, which will make this thing something like this. And the final state will be something like this. Okay? So that's how we break down the angular deformation and the rotation. This notion where we break down a regular thing into a symmetric one and an anti-symmetric one is a very important notion in mechanics. Maybe you have encountered that notion in, say, structural analysis. Okay. So now we get the two tensors, right? First, we have the deformation tensor, or to be more exact, deformation rate tensor. Deformation rate tensor. We call it D for deformation. This is just the tensor formed by all the epsilons. So we have linear deformation on the diagonals, and we have angular deformations on the other entries, for the other entries. I won't write them anymore. You get the idea. Okay, so this is called the deformation rate tensor, and this tensor, as I have said, is a symmetric one, right? Also, I'll tell you that the deformation tensor is just something like this. You remember this thing, right? Between the nebula and you, I didn't write anything in between, so this is the velocity gradient, right? The velocity gradient. So I claim that the velocity gradient plus the velocity gradient transpose we know that the velocity gradient is a second order tensor, right? So its transpose will also be a second order tensor, so they can add to each other. Okay, so I claim that this thing is just equal to the deformation rate tensor. You are welcome to check that fact because we know how to calculate the velocity gradient, right? Also, we can see that from here, we can see that the deformation tensor is indeed a symmetric tensor because we know that any matrix, if added by their transpose, we will get a symmetric tensor. Okay, so this is the deformation rate tensor. Now let's talk about the rotation. The rotation, we can also pick them all out to form a tensor. So the rotation tensor, we'll call it to be omega. And as I have said, the omega tensor is a anti-symmetric tensor, which means omega ij will equal to minus omega ji, right? Minus omega ji. On the diagonal, we'll have zeros. And on the other entries, we will have the rotations, right? So here I want to write omega 1, 2, but I'll offer you another notation, which is just call it lowercase omega 3. Lowercase omega 3. You can just treat it as a definition, okay? Omega 3 minus omega 2, omega 1 minus omega 1, minus omega 3, and omega 2. So you can say you can see that the omega tensor is indeed a anti-symmetric tensor, right? Why don't we have anything? Why do we only have 0 on the diagonal? Well, in order to introduce the notion of rotation, at least you need 2 directions, right? If you just have 1 direction, you cannot rotate, right? So that's why if only 1 direction involved, we cannot have anything like rotation. So this is the rotation tensor.